Hi. So, you want to run a multiverse analysis. Maybe you've seen one of the many papers that have reported this kind of analysis. Maybe you're a bit apprehensive about the amount of coding that goes into it. After all, the idea of running tens to hundreds of thousands of models and extracting the results could sound like a very daunting thing. I've worked with these a little bit now, enough to have programmed a few from scratch, and I wanted to kind of share how I've done this a couple of times, just to give you an idea about how sort of low the entry level is, particularly if you already know a bit of R, which I'll be kind of running through in this video. So one of the real powers of multiverse analysis is running a large number of models that you can then extract information from, usually the statistical results, in order to investigate the kinds of decisions that influence the model in powerful ways, or perhaps not, and also the distributions of effects is a really powerful thing to look at. So what we'll be doing is looking through some data that I took from openpsychometrics.org. I just grabbed the 16pf one. I think it's the first one on the website itself. And you can find all of the code on my GitHub here at the top. In the README file, I'll also link to a bunch of papers. I'll send you over to the code for the cognitive task reliability multiverse in my split half R package. And feel free to drop me a message on any of the places where you can find my information to talk about this a little bit more. I think this is a really powerful methodology and it's really useful. Now what we'll be running through in here is kind of two very simple approaches to extracting information from linear models, regressions, in order to, as again, run many models, extract the information. There's so much more that can be done with multiverse, for example, branching into specification curve analysis in order to test against a null model the distribution that you've generated, or alternative approaches entirely, so like vibration of effects and so on. So to that end, we'll briefly kind of go through a few basics around this, just for those that haven't used R that much. I want to try and lower the bar as much as possible. I will try and keep it fairly short as much as I can. If need be, I'll split this into two videos so that the more complicated version gets a little bit more time. And I'll try and explain as much as I can as we go. I'm going to try and do this in a live coding way just to give you an idea about partly how simple it can be to put this together from scratch, but also just some of the things that are likely to pop up that are really easy. Not necessarily mistakes, but just things that can happen when we program this kind of thing. So first things first, I'm going to load in the tidyverse, lmbeta, and patchwork packages. I basically always load the tidyverse. That's just part of my workflow now. In this case, largely it's for the dplyr package as well as the pipe operator. The lmbeta package will be using the lmbeta function from to extract standardized effect size estimates from regression models or from LM models. And the patchwork package is amazing, and we'll be using that to help us plot our multiverses, because there's a lot of art in science and I like to make the most of it. The data itself is actually along with the code in the folder 16pf, so you can load that with the read.delim file. The first time I coded this, I tried read.csv and it didn't work, partly for reasons that I'm not entirely sure of. So let's do a quick reminder of the LM function. So the LM linear model, run regressions, nice and simple. So what we're going to do is load our data into it by specifying data equals det, and we'll then specify the formula for our function. You don't have to specify formula equals. I find it useful when we get to the later stages, and a lot of the things I'll show in this next section I'll mainly be showing because they'll be useful later on. So let's say, for example, within this data set we have a bunch of variables. Honestly, I have no idea what they are. I'm sure it's a very interesting data set. It's just not within my remit. And what I hope that this video does is give you an idea about how you can use this approach and adapt it to your own circumstances. So in this case, there's variables A1 through A10, B1 through 10, and others. I assume that they correspond to particular measures, but for our purposes here, it doesn't really matter. Now in this case, we can run our LM model, and we get this output here in the console, but there's not much here. If all that we wanted was the unstandardized effect size here, great. We can save that and use it. What can make this a little bit more useful is to save the object in general. I like wrapping it in summary because we get all of the summary information. Let's change the size of this so we can see it just a little bit better. So in this case we have residual information, we have information about the coefficients, so both the intercept and in this case the A2 predictor. Things like the p-values, the r-squared estimates, and so on. What's nice is that we can use this to extract, for example, single bits of information that we might be interested later. So for example, when we run the multiverse, we might only be interested in the r-squared from the model itself, or from a large number of models. So in that case, we pull out the r-squared and we get this. And that can be really useful. An extension of that, for example, if we had a list of these, we might want to save it into something. So let's say this is our first model, we'll call it model 1, and this is the r-squared for it. We can save it into this object, and if we call that later, we can pull it out. Now there's going to be lots of different ways that you can do certain aspects of these models. In my book, there's not really a right or wrong way. There's ways that could be more error prone, there's ways that might make things easier for you, and I'll try and point those out. But there's also going to be many ways to call these for this information. Okay, now what we can also do, so we've saved the summary here, but let's say that we want to change that and save the full model output. So in this case, we're going to just copy and paste for the sake of quickness. We're going to run the model and save it in this model1 object. And what we can then do from this lm beta package, we can run lm beta. We can put model1 into it. Let's expand this. Now if we run this, you can see how we get standardized coefficients now, just here. Now that also comes out when we save the model. For example, if we call this model1 standardized. Now that we've saved the object, we can also explore it, which is quite nice. So we could use, for example, view, and we'll call model1 standard, and this will pop it up in our Explorer. So within here you can see we've got the coefficients, the residuals, all the information that we normally had, and we've also now got the standardized coefficients here as well. Now this is really useful, and we'll make use of this later as well. Okay, now let's move into the multiverse itself. That's why we're here. That's the thing that we're going to have the most fun with. So let's say, for example, we wanted to predict, for reasons unknown, the first beta, or the first B variable, so in this case b1, we're going to see which of the a variables predicts that best. So for the sake of speed, let's just copy this predictors list from my other screen. So within the dataset, there are 10 a variables. We're going to see how well each of these predicts, in this case b. Now remember up here, we have the formula for our linear model. We can put that in as a string, which is really useful. So let's create a list of strings to do that. We'll call it predictors formula. Normally I would use shorter names for ease, but never mind. It doesn't really matter for just now. So what we're going to do is paste together. So this is our b1 is predicted by, and we're going to paste that to our predictors. So now, oh, my mistake. I hadn't run predictors, so we're going to run that. We're now going to run predictors formula. It's going to give us that paste. If we run just predictors underscore formula, that's going to now give us our list of models. So we're going to run b1 is predicted by a1, b1 is predicted by a2, and so on. Now to run that, what I'll do is, rather than giving the full code from start to end, I'll kind of show you how I would normally build this up myself. So first things first, as before, we're going to run our linear model. We're going to run plug the data into that, and our formula is going to be from predictors formula. Now it won't work if we run it as it's currently running now. So what we're going to do is wrap this in a for loop. You will find I use for loops for basically this whole thing, partly because I think that's an easier entry point into running these kind of models, particularly if you're not used to running analyses in R, for example. Also, I think it's a very readable way of running these analyses. As I say, there are many other ways of doing this. People will argue that other approaches, for example, the apply family, will be quicker, and there will be ways of making this run more quickly. In my experience, though, you can run thousands of linear models within R in a few seconds, so I'm not really that worried. Okay, so let's build our for loop. So we're going to do for I in, it's always I don't know why, it can be anything. I just seems to be the convention that I've seen before and that I've fallen into myself. So we could run for I 1 in 10. This 1 in 10 is going to then correspond to our 10 predictors. So actually what I'm going to do is end this with the length of the predictors. So what that's going to do is give us a list of 1 to 10. So we're going to run this for loop 10 times. And while we're in the for loop, we're going to use that I to index our current loop. We're going to wrap everything that's in the for loop in these nice curly brackets. So it's going to run through this for each one of the values in this list. Now, the important thing about that is that we want our predictors formula to correspond to our number in this list. So we can do that by adding square brackets I. So each time we run through this, it's going to take the ith value of the predictors formula. So for example, at first it will take b1 as predicted by a1, then it will take b1 as predicted by a2, and so on. Now that's going to be useful, but we don't want to run this without saving it into anything. So what we'll do, I'm just going to call it out for ease. The problem, right now at least, is that if we save it like this, it's going to overwrite this out every time. So let's create out as a list. My experience is it basically has to be a list in this respect because the LM object is a list itself, so you're kind of creating a list of lists. It doesn't really work as a vector. And because of that, we need 2 square brackets with the I here. Now, running all of this should, assuming I've not made any mistakes, run your 10 models. If then, for example, we were to run view out, we'd be able to find our list of 10 models. Within each one, we have all of the outputs. So that's quite cool. Now, before we do anything else, let's say that the thing that we're interested in extracting from these models are the standardized beta for the predictor and the R-squared for the overall variance explained. So to do that, what we'll do first is we'll save both of those into variables. So we'll call it our R2s, which we're just going to make empty just now, and our standard betas, which we'll also just make NAs just for now. Now what we want are both of these appearing within our for loops. Again, similar to out here, we're going to want it to load into the ith position in that, in this case, vector, I suppose. Because it's not a list, we only need the 1 square bracket. So let's add those in first. Now, remembering what we had done before, we can take this LM object. So actually, we'll just take out. So for the R-squared, what we can do is take summary, so for all those summary statistics that we found earlier, and extract the R-squared. The standardized beta, I have to remind myself about every time. So using my cheat sheet, what we'll do is we'll run lm beta. We're going to run that on the output itself, so on the model. Now what this does is creates an output that includes the standardized coefficients as well. So, just because my spelling is awful, we'll add standardized.coefficients here. Now, because these models end up with the main predictor and the intercept, actually will only be after the second one, and that will correspond to whichever the predictor is. So now we can run this. So that ran fine. We'll assume it ran fine, and I'll create a data frame for us to plug that into. I'm going to call it out table, just for ease of my own idiosyncratic way of doing things. Okay, so within data table, what we're going to grab is our predictors. We're going to extract the R-squared from each of the models and the standardized beta from each model. Okay. Oh, my mistake. Data table is a specific package that I know a lot of people are very happy with. I'm just going to run it into a data frame for ease. Okay. Now, one of the important things we're going to start to think about is plotting the multiverse. So the first thing that we'll do is just double check what the out table looks like. Let's make that a little bit bigger and run out table again. So you can see for each predictor in order, we have the R-squared from that, that run, and also the standardized beta for that as a predictor of B1. Again, these values or these variables could be anything. So what we'll do first, this could be done within the same data frame, but I have a preference of creating a new one, just because in my own experience, my coding goes horribly wrong all the time, and it's kind of nice not to have to rerun everything if not necessary. So what we're going to do is order out table by, in this case, we'll take the standardized beta. So we'll run out table within the square brackets. We're going to organize the rows. So we're going to, this is why live coding's good. You can see me doing terrible things to my code. We're going to order our out table. We're going to order it by the standardized beta column. That's fine. Let's not forget our little comma within the square brackets because it's a data frame. So we're going to run that. That's going to put everything in order. Now what we're also going to do is create a n variable that's literally just going to be the numbers from 1, in this case to 10, but the number of rows. So we're going to run that without table 2. And this is going to be useful because we're going to use n to plot along our x-axis in our functions. So let's start to think about plotting this multiverse. So if you don't use ggplot, I highly recommend it. It's really pretty, it's awesome. There's a lot of functionality and a lot of flexibility within it. It's really cool. So let's grab our outtable2 object. That's the data that we're going to load into it. We're going to specify our aesthetics. So on our x-axis we can have n, so that just means that all of our models are going to be in order of the size of the standardized estimate. And then on the y-axis we're going to plot our standardized beta. Okay, so that in itself sets up the object, but to actually plot something we're going to add a geom. In this case we're going to add a point. So what this will do is just plot a point for each standardized beta estimate, basically a scatter plot. So you can see down in the bottom here we have, for each model, we have our standardized beta. Great. In a more complicated version, what you might consider doing is running, for example, a bootstrap or extracting confidence intervals around this so that you can have confidence intervals as well. You can check out the code in my split half package, for example, that does that for bootstrapped reliability estimates. So what I'm going to skip through is making this plot a little bit prettier. Essentially, I just removed some of the labels and set some of the theme aspects to just be a little bit nicer. This will be more relevant later. Now I'm going to save this ggplot object so that we can use it later on within Patchwork to plot it with our dashboard. So normally, at least in my experience, when plotting a multiverse, it's useful to plot both the distribution of the estimates that we've already done, but also the corresponding decisions that led to that estimate. In this case, which variable you chose as a predictor. So to do that, we'll just restructure our outtable2. We're going to call it outtable3. So we're going to pipe our outtable2. So what this is going to do is push that table into the next function, which is going to be gather. I highly recommend looking into the pipe operator and the tidyverse, tidy data way of doing things. It's really nice. You can do a lot with very little code. So what I'm going to restructure this as is into two main variables that code the decisions made. Now this will be more important in the next example when we're not choosing simply between which predictor, but we're choosing among a list of predictors whether we're going to include them or not. So in this case, that would correspond to our big decision is the variable itself, and the decision is which of variables within that decision do we include. So for example, in this case it won't make any difference to our plot because our only big decision is what do we include as our predictor. Whereas in our later example, the big decisions will correspond to, for each variable, did I or did I not include it? And then the decision is, did I or did I not include it? Now the way that I code that later, the do not include it just ends up as an NA, so we'll also remove NAs later on. Now to make sure this works properly, we're going to just get rid or force gather to ignore our variables. What gather does is basically turn wide data into long data. So instead of having columns be different variables, each row can be a different observation, a different variable for each participant. And just for ease, for quickness, we're going to pipe that into filter and remove NAs, just to be extra sure. Okay, now we can do the fun bit. So we're going to make a panel that corresponds in order. There we go. A panel plot that corresponds in order to our models and the variables that went into them. So in this case, our data is the out table 3 that we just created. Our aesthetics, we want our x-axis to still be n, and our y-axis is going to be decision. To keep this one simple, in the next example we'll add in color, and we'll color it by big decision, and we'll plot them as facets, but for now it doesn't matter. Okay? Now we're going to use geom point. We're going to change the shape of the points to be a vertical line because it just comes out a bit nicer in the plots, but of course you can do pretty much whatever you want. And just so you can see a bit better, we'll change the size arbitrarily to 7 right now. So as you can see here, we have a plot that in order of the standardized beta, which variable was in there. Now we can set this so that it orders properly 1 to 10, but for now we'll ignore that. So we can see that the variable with the highest beta was predicted by A2, secondarily by A4, and so on. But what we kind of want is both of these to go together. Again, what we'll do, same as I did earlier, is just copy in some aesthetics, some theme stuff to make it a little bit prettier. In this case it does very little, but it'll be more important later. I'm going to save this into an object called dashboard, just because this part of the plot's been described as a dashboard. Now using patchwork, which thankfully we don't have to call or do anything really fancy with, we're going to specify MVP, so our multiverse plot, over dashboard. And basically there we have it. So what's really nice about this is that if we kind of move vertically, each of our decisions on the bottom plot corresponds to a particular effect size or standardized effect size estimate at the top, and we can clearly see which decisions correspond above. In the next example, we will have more decisions as to whether variables are included or not in predicting another variable, and this will be even more useful, hopefully. Okay, so that is a very quick, very first multiverse. The second part of the video should be very short. I'm going to include it just as a single video and hopefully put timestamps in. So let's make this a little bit more complicated. Let's say we still want to predict our B1 variable because it's super important to us. But what we want to do is create a series of models that can include any combination of these A values as predictors. So we could include, for example, only A1, or we could include A1, A2, A3, A4, and so on. But what we want to do is include all possible combinations, assuming that we don't have some kind of a priori reason for not including certain combinations. The way I've coded this is slightly different. To make it a little bit easier to see, I'm going to copy this in and just talk about it. Okay. So what we're creating first is a list of predictors that we're interested in. And we're going to use this with expand grid next to create a table of all possible combinations from this list above. So this is going to correspond to the decision, or the big decision, of do we include variable A1? In this case, NA was just the easiest way for me to code this. I'm sure there are other ways of doing it. So in this case, we're going to code either we don't include the variable, or we do include the variable. And very shortly, what we're going to do is combine these similarly that we did with paste earlier to create our variable. Except this time it's going to cover all possible combinations. So if we run both of these, now let's just, to show you what this predictor grid looks like. So we have a grid that for each possible predictor, we code whether we do or don't include it. If it's included, we do include it. Now the first row is going to be only NAs, so that we don't try and force our linear model to only include NAs or an entirely blank formula, we're just going to do predictor grid, and we're just going to remove the first row. Easy peasy. Now, again, for some of these things, I like to just create a new variable and just add a 2 on the end of it, just for my own, I guess, peace of mind. Now, what we're going to do with the predictor grid is pipe it through a tidyr function. Now, unite is the function. It comes from tidyr. Loading tidyr and dplyr from tidyverse can clash sometimes, and unite exists across a couple of packages. So a nice kind of trick that you can do within R is these, the double colons. If you run that, then you can run this function directly from the package without having to load that package, which I find really useful. So we're going to create a variable called formula. And what that formula is going to comprise of is everything from A1 to A10. We're going to separate each of those with a plus. And really importantly, because I forgot this several times and it ruined everything and cost me a lot of time, is we're going to set na.rm to true. So this will ignore the NAs that we've created, and so we will only have, for example, A1 plus A8 rather than A1 plus NA, 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 etc. A8. Okay, so if we run predictor grid 2, let's just change that. My mistake. So I forgot to put sep equals. So sep equals just means that when we include the variables, they'll be separated by this plus. My mistake. So now what that looks like, if we were to view it, are, for example, these lists of variables, so A4, A6, A7, A8, A9, A10, etc. And we're going to use that to predict B1 in the formula for the function itself. So what I'm going to do differently this time is run all of the models within a single for loop, and then we're going to use a different for loop to extract the information that we're interested in. I personally think that's a nicer way of doing it, because it means that you can run all of your models and then kind of figure out what you need to do with it afterwards, make changes to the extraction from those models, and it means that you don't have to rerun all of those models later on, which can be quite useful. So I'm going to call this list output through sheer lack of imagination. List. There we go. So then we have our for loop. Within that for loop, so 1 to n row. So we've got a list of the number of rows in this case, the predictor grid 2, which I believe we have just over 1,000. We have 1,023 possible combinations. So for each of those runs within our for loop, we're going to save our model into the Outlook list, and our model is going to look something like this. We're going to run a linear model on our data equaling dat, and our formula is going to look something like this. So we're going to paste together. Paste just puts together strings, creates strings out of objects. You can do a lot of nice fun things with it. So we're going to predict B1, and we're going to predict it using the formula that we had before. So what we need to make sure is that we're extracting the formula that corresponds to that particular row, so that we can then combine this output, sorry. You can tell I've been running emails today. Output. We can run this on each of the relevant models. So we're going to take predictor grid, and then in our single square brackets we're going to put I. Now, as far as I'm aware, predictor grid doesn't have any other variables in it. Let's just double check. In fact, sorry, we created formula. So what we're going to do is make sure that we're running for the ith column. We're going to extract from the formula variable. Okay, so now we should be okay to run this. Now, you'll note this takes a few seconds longer than before, just purely because we're running 1,000 models. However, it does look like it's already done. So let's, similar to what we did before, let's just quickly view our output object. And it may still be running, which is fine. As I say, it's running 1,000 models. It shouldn't take too long, but this computer's just running a few different things in the background, including actually running the models themselves. So, let's double check that it's in here. Not yet. Okay. So we are still running our models. Perhaps I should have taken a subset. That's neither here nor there. It's not important. Okay, so while that runs, let's set up our extraction. Oh, there we go. So we have thousands of models. For each model, we have all of the output, and we're going to extract from that output. To extract from the output, we're going to use for loops. There are nicer ways of extracting information from lists like this, but to keep it as simple as possible, let's just do it that way. So let's say, for example, we just want to know what the best fitting model is, so we're going to extract the R squareds. So what we're going to do, we're basically just going to copy this, because the for loop is going to be much the same. We want it to correspond to the same rows, etc., etc. But in this case, what we want to do is capture for the r-squared object. Let's extract the summary data from the output object, and what we're specifically interested in is the r-squared. Okay, so let's run those. This should run much quicker because you're just extracting information at this point rather than collating information. So you'll see if we view r-squared in the console, we just have a list of r-squareds here. Okay, so we're getting closer and closer to this plotting. In fact, we're getting very close now. So I'm going to call our final set of objects final. We're going to combine our predictor grid, so our yes or no, are these variables included, with our r-squareds. Now, similar to what I did before, we're going to take this final model, create another one, and we're going to order it. And we're going to order it by the r-squared. And don't forget the little comma there as well. Let's run that. And let's not forget to also plug in a n variable that's just going to be our 1 to n row final 2. Again, that's just so that we can order everything, and it's a bit nicer in that respect. Okay, so there's different ways that we might want to expand this, but let's just dive straight into the plotting of the model. So you saw it earlier. I'll do this in a copy-paste way so that we don't quite have to live code everything. So again, we're taking the data from final 2 that we just created. We're using n for the x-axis, the r-squared for the y-axis, and geom point. Exactly the same as we did before. We're going to call this MVP2 and run that. Now, let's do a little bit of restructuring. Again, the same as we did above, we're going to restructure our final 2 objects by the big decision and the small decision. In this case, each big decision, we can ignore this, that's fine. Each big decision is going to be each variable, and the decision is going to be whether you chose to or not to include it. And we don't want to have the NAs in, basically. So we'll get rid of that. One thing that's useful to mention, that again I'll just kind of copy and paste in here, is that we want the factors for our big decisions to be in the same order as the variables themselves, so a1 through 10. So this should do it, I hope, by specifying the factors for that. Now what's a little bit more complicated than before is the way that we're going to set up our dashboard. We'll call it dashboard 2. Once again, we're creating a ggplot object. In this case, our data is going to be final 3. Our aesthetics are going to be x. On the x-axis we want n. On the y-axis we want decision. And because we have the decisions within the bigger decisions, what we're also going to do is color that. So in this case, we'll see a colored bar, and it will be a different color for each of the variables. So we're going to specify color as our big decision. And that's underneath the aesthetics. Now we want these big decisions to be in different grids. Just makes it easier, makes it nicer to plot. We can do that with facet grid. I am just going to copy and paste that in because it took me a while to figure this one out. So the formula is big decision by everything else, signified by the dot. So this just means that within that dashboard, each variable is going to go in at a different slot. And scales free, space free, drop equals just kind of helps make it a bit nicer. As we had before, we're going to do a geom point. Just as a kind of reminder for the aesthetics, we're going to keep the color as the big decision. And we're also going to have the shape be that little vertical line. And I'm going to assume that a size of around about 7-ish is probably going to be okay. And then everything else is just a few of the options that we've used before to make things a little bit nicer around the plotting of it. So we have this dashboard, we can run that. Within Patchwork, we can then again run our MVP2 over dashboard 2. And that is going to give us just a very pretty plot. Here we go. So there's many more objects in here. What you might want to do is only present, for example, the lowest 100 and the highest 100 and maybe a random sample from the middle. It's easily enough done with some restructuring of the data. But what this does give us an idea of are the exact specifications that that correspond to that particular R-squared estimate. So for example, in the lowest estimates, we can see that actually not many variables were included, and they tend to only be these kind of higher ones. And we can see that at the higher end, the estimates tended to include most of the variables. And that's a really useful thing just to think about as well. If you vary the number of predictors within this, you will also need to include that information in your interpretation of the distribution of effect sizes, or particularly for variance explained here, because we would expect more variance to be explained if you include more predictors. But that will be another video. I hope that this has been useful in some kind of quick insights and starting points on how to run multiverse analyses. Ultimately, I think once you've managed to program your first one and kind of interpret it and get a bit of a feel for the kinds of information you can get out of this kind of approach, I think you'll find that there's a lot of fun things that you can do with it. Partly there's something really satisfying about getting just this really cool plot out, and something just really satisfying about running all of the models. Always run all the models. I guess a caveat, please don't use this kind of approach as a sort of p-hacking tool. Its purpose is to give you a distribution of effects that you can use to interpret, possibly run further analyses on itself, and get more information about the kinds of predictors that will influence your model. It's not a way to, for example, pick this model at the very top and decide that it's quote-unquote the right one because it predicts the most variance and will be significant and blah blah blah. I plan on recording a few more of these videos in the future to try and just share what I hope are some kind of useful starting points for some programming. If you need a quicker introduction to this, as I said at the very start, all of the code and the data are on these two links that will also be in the video information. If you've stuck with this video for the full, getting on 50 minutes now, thank you for watching. Give it a like, I suppose. I hope that it was useful, and thank you for watching.